All right. I would like to pick up where we left off in the 9-1 notes because I said I really do want to get through 9-1 before the long weekend. Your tests are already done. I was just amazing. Got them done already. I will put them in the computer, but I can probably even remind me, I'll give them back at the end of the hour. We'll talk more about it though after break, okay? Because I want to, there are some things I want to talk about, but I want to make sure we get through 9-1. All right, just a reminder, your vocab and tech page here, we do have a lot of new vocab, especially in this section, and you are going to be learning some new things on the calculator. That's one thing I will remind you is when you do those things on the calculator, the one proportion Z test, the one sample T test, or the confidence intervals, you need to name them. You don't need to name when you're doing inverse norm, okay? But, all right, so where we left off here, we were talking about the beginning of hypothesis testing, also called significance testing, and we talked about how to set up our null and alternative hypotheses. We have one-tailed versus two-tailed tests. Make sure that you are always defining whether it's a population proportion or a population mean, what it represents each time. And we are now actually getting into how do we decide how small does a probability have to be in order for us to reject a claim. And I think we walked through this the other day, did we? I think, okay. 3 common values for alpha, which is called your level of significance. We have 1%, 5%, 10%, which not a coincidence. We talk about confidence intervals of 90%, 95, and 99% are our common ones. All right. When your probability comes in smaller than your predefined alpha, that's when you will reject the null hypothesis. Never say you proved anything. Don't even use that word in here, okay? You have evidence to support. We have sufficient evidence to reject the claim. We don't prove anything. I mean, think about it. You take one different sample. Couldn't the numbers come in differently? Yes, okay? And when you're asked to interpret a p-value, here's a phrasing that you can kind of sort of memorize. All right, the next page. I redid my notes and I was moving things around and this whole section got repeated. So we just talked through that, so get rid of that. What I want to do now is I want to talk about that basketball example again. So what we started with, we did an exercise and I started the notes by saying, there's a guy who says, I make 80% of my free throws. So you're like, prove it. He stands there, he takes 50 shots, he only makes 32. He comes in at 64%. Okay, that is definitely lower than what he said. But the big question is it significantly lower from a statistical perspective that we could say, wow, that is so low that I don't believe you? Or do you say that, yeah, it's low, but maybe you just had a bad day, okay? That's what we're getting into. So what I did now is I changed it. I said, let's say he made 36 out of 50, okay? So he still came in low. He came in at 72%. But again, is that so low that you're going to come back and conclude, see, I told you you're not that good? Or do you come back and say, all right, maybe you are an 80% shooter and you just had a bad day? So we're going to take a look at this and we're going to look at the 3 common significance levels, okay? Now, I'm telling you that if you actually did the math on this, and you'll learn how to do this eventually, but I'm telling you that the p-value for this scenario would come out to be 0.0786, so about 8%. So what this would be saying is, assuming the guy really is an 80% shooter, the chances of him coming in at 72% or lower, just due to random chance, is 8%. Okay? What you do, you take the p-value and you ask yourself, is that smaller than alpha? And you'll see me write that all the time. You're going to take that 0.0786 and you're going to say, is it smaller than 0.01? And of course, your answer to that should be no. In this case, you would say, I failed to reject the null hypothesis. Now, you do that in context of the problem. So the null hypothesis is what we accepted to be true. We were going to believe the guy 80%. In fact, this would now come back and say, fail to reject. We have no reason to reject his claim. Yeah, you came in low, but you didn't come in that much lower, so okay, you had a bad day. Now, if you had decided to use a 5% level of significance, is that P smaller than that alpha? Well, the P doesn't change if we're in the same situation. No, it's still not smaller. Fail to reject the null hypothesis. You would still have to come back and say, okay, you didn't make 80%, but I guess you had a bad day. But look what happens if you switch to 10%. If you were doing this problem and you said, is P smaller than alpha? Is 8% smaller than 10%? Yes. Now we would reject the null hypothesis. So now what we would do, and I'm just going to flip back for a second, you would be rejecting his claim of 80%, and we would be saying we now have evidence to support the fact that your true percentage is actually smaller than 80%. Okay? Now, this seems weird to some people. They're like, well, so I could make alpha whatever, and then I could always make it so that it either rejects or fails to reject. That's the reason the confidence level should be selected before your data collection. Okay? You should not be waiting until the results come in, and then you go back and say, oh, the results came in at 8%. Oh, I'm going to say I was doing 10% then so that I can reject your claim. You can't do that. Okay? You set your alpha ahead of time, and you decide, because again, it's kind of related to confidence. You decide how confident you want to be, how restrictive you want to be, and you set this ahead of time. Okay? Now, this is the way your book does it. This is called the p-value approach. Okay? I do want to show you something else called the classical approach. They do the same thing, but every once in a while, I've seen questions on the AP exam that if you know the classical approach, it's a little bit easier, okay? So the classical approach does this, okay? So forget about all this. For each one of these, what you would do, you would say, okay, 1%. What you would do is you would mark down here, you would mark, and I'm marking this way over here because I want this little tail to only be worth 1%. So you're going to make that tail really tiny, okay? So this tail is sometimes marked as Z sub alpha equals 0.01, or sometimes people just call it Z sub 0.01. If you were to do the classical approach on this one, you would mark a tail at 5%. So make that one a little bit bigger. So we would call that Z sub 0.05. And if you were doing the classical approach on this one, you'd make the tail a little bit bigger because now the tail has to be worth 10%. So Z sub 0.10. So when you're doing the classical approach, you always start with the diagram and you just mark your alpha, okay? So every problem you would do would start with the same drawing. But then what you do, when the results come in, when the result of 8% comes in, well, if this is 1%, think of this almost as like an x-axis scale. If this is where 1% is, 8% would be way over here. You didn't land in what is called the critical region. and that means it's a fail to reject. If you have a 5% tail marked, and then you've marked 8%, you still failed to fall into the critical region, so it's a fail to reject. But if you have a 10% tail marked, and you mark an 8%, you just landed in the critical region. And someone we talked about this actually my 4th hour yesterday or 2 days ago, and someone summed it up really well. She goes, so in other words, you're saying that 8% is so tiny that you're far enough off in the tail that you're like, oh my gosh, that is so improbable. Exactly. Okay, if you set up a 10% level of significance, we're saying that 8% is rather improbable, and therefore we reject the null hypothesis. Okay. I don't care which method you use. This is the one that I will consistently use. The first year I taught this course, I did not teach the classical approach. And when we got into AP review, there were a couple problems. I'm like, oh my gosh, I said, you guys need to learn the classical approach. And I had to go back and teach it at the end, okay? All right, so unfortunately, a lot of the stuff in the notes now is talking through some stuff. So I don't know if it's already kind of hit you, but I keep telling you that you haven't proven anything. But that bothers some people. They're like, well, but then how do I really know? And it's like, sometimes you don't. And sometimes you will know, but something happens later, okay? There are mistakes that are made when you draw inference, okay? All we can do is collect the data, make decisions based on that data, and we hope that we're making the good choices. But when you draw a conclusion, you hope it's correct, but there's no guarantee. In fact, there are 4 things that could happen. And you can think about the basketball player if you want. Let's say we reject the null hypothesis in favor of the alternative. So we tell him you are not an 80% shooter. Okay? And then you find out that the alternative hypothesis is true. So you made a good choice. You said you are not an 80% shooter. You are only a 64% shooter, or at least you're lower. Fine. So you were right. That's good. I'm going to jump ahead to this note. But what if you reject the claim and you tell the guy you're not that good, and you find out later he really is, that he really did just have a really bad day? Okay. You made what's called a type 1 error. Okay. Type 1 is when you reject the claim and you say you're a liar, and you realize later you were wrong. You made a type 1 error, okay? What if you don't reject the null hypothesis? You come back and you say, okay, you might have had a bad day. You're all right. I believe 80%, okay? So you don't reject the null hypothesis, and you find out he really is that good. Okay, good. That's good. It's another good decision. You didn't reject it. He really is good. Great. But what if you don't reject it? You say, all right, you're an 80% shooter. And then you start watching him play more and more, and you're like, dang, no, he's not. Okay. So if you trust him and you believe him, and then later on you find out, wow, I shouldn't have believed him. That's a type 2 error. Okay. So I made up this thing the first year I taught this course. And when we talk about we do not reject, we often will phrase it as we fail to reject. We fail to reject. Okay. Failing to reject means you're staying with it. You're staying with what someone tells you. You're going to stay with the claim. I'm an 80% shooter. Fine. I believe you. But what I do is if you find out later that that's wrong, I think about the word 2 and I change it to the number 2. Okay. If you fail to reject and you realize later you made a mistake, you made a type 2 error. So if you fail to reject, you believe the guy, and then later on you find out he sucks. Okay, you made a type 2 error. Fail to reject, type 2. All right, so this is the diagram they have in your book. So what we have here, if the null hypothesis is true and you fail to reject it, this is good. I'm going to put a smiley face here. You fail to reject it, you believe him, and you watch him play over and over. It's like, wow, he really is good. All right, that's good. Now, what if you say, I don't believe you, I'm going to reject your 80%, and eventually we find out that, wow, yeah, see, I was right to reject that because you're not that good. Okay, that's another smiley face. That's a good thing. You didn't make any errors. You believed him and he's good. You don't believe him, he's bad. Okay, that you made the right choice. But if you reject his claim and then later on you find out it was true, okay, you just made a mistake. That's type 1. And down here is fail to reject. You believe him. And then later on you find out he's not that good. That's a type 2 error. Okay. All right, so let's talk about, let's do an error example here. Potato chips. A potato chip producer and its main supplier agree that each shipment of potatoes must meet certain quality standards. If the producer determines that more than 8% of the potatoes in the shipment have blemishes. I'm not sure what that means. Maybe bruises. Maybe there's a little eyeballs on the, no. You know, potatoes get those little eyes on them. They're so gross. Okay, whatever. If they determine that more than 8% of the potatoes have blemishes, they are going to send the truck back and get a different load from the supplier. Otherwise, the entire truckload will be used to make potato chips. To make the decision, a supervisor will inspect a random sample of potatoes. I mean, can you picture they have a big old truckload? They can't inspect all the potatoes. They're just going to do a random sample, okay? So the null and alternative hypothesis would be, all right, the number they gave us here is an 8%, 0.08. That is a percentage, a proportion. We're using P's. So the null hypothesis has to use P for percentage. The null hypothesis always uses an equal sign. And we're going to use the number of 8%. Now, the alternative hypothesis has to use the same variable P. It has to use the same number, 8%. But now you have to choose. Do you want a less than, a greater than, or a not equal to? If the producer determines that more than 8%, greater than, those are your null and alternative hypotheses, where P stands for the true proportion of potatoes with blemishes, whatever that might mean. That's how you write null and alternative hypotheses. Okay? Think of it as 3 parts. There's H sub O, H sub A, and define your variable. And never use a P hat or an X bar here. You either use P or mu. All right. Describe a type 1 error. Now, type 1 error is you reject the null hypothesis and later find that H sub 0 or H sub O, the null hypothesis, is true. Okay, now that's the general definition of type 1 error. You are not allowed to do that on my test or on May 5th. In context, if we say we reject the null hypothesis, if you're rejecting, you are rejecting it in favor of supporting this. So if you reject the null hypothesis, you would be saying that you believe more than 8% of the potatoes are bad. And because you believe that more than 8% are bad, what are you going to do? You send the truck away. Now, they will literally ask you to do this on the AP test. They will ask you sometimes, describe a potential consequence for this. This is you using common sense. Okay, think about it. You work for this potato chip company. A truck comes in. You say your potatoes are horrible. Send them back. What does that mean to you as the businessman? Guess what you're not doing right now? Making potato chips. So what's happening at your company? Everyone is just sitting there waiting for the new potatoes to come in. You are losing time. You're losing money. Okay, losing time and money. You're wasting your human resources. They're sitting around. Okay, it's like the auto companies right now. They're sitting around waiting for the chips to come in. You know, it's every bit is lost time and money. Now, a type 2 error. Again, type 2, if you want to just define it in general, type 2 is you do not reject. You fail to reject the null hypothesis. So you stick with it and later find it's not true. So in other words, you don't reject this in favor of this. If you're not rejecting the null hypothesis, you're sticking with it. You're saying the status quo is good. So in this case, what you're going to do is keep the potatoes and make the chips. Now, what does that mean about your potato chips though? If you're using bad potatoes, you ever open a bag of potato chips and they're like all brown and stuff? Eat the brown ones. I don't like potato chips much anyways, but I don't eat the brown ones. If I eat Lay's potato chips, they're going to be like the light, fluffy yellow ones. Okay. So again, describe a type 2 error in this setting. You keep the potatoes, you make the chips. The chips are bad, and the customers now get mad. I opened a bag of scoops once. You know what scoops are, right? The little Tostito things. I swear I should have done like a statistical sample on it. They were all flat. They were a whole bunch of them were flat. It's like I did not get scoops. I just got little nacho chips. I was pretty mad. Okay. So in your opinion though, which would be worse? Which do you think is worse, type 1 or type 2? Think type 2? You don't want to make the customers mad, because if the customers get mad, now they're not going to buy your chips in the future either, right? I would probably say the same thing here. But there's not a right or wrong answer. Again, if that sort of thing came up on the AP test or my test, just use common sense. So if you believe type 2 is worse, explain why. I think the customer's going to be angry and now I lose customers for the future. Okay. I would rather that I just had to sit for a while so I can ensure that my chips are better. See, the thing is, there's not one right or wrong rule about which is better or worse. And that's what I have on the next page. Okay. The type of error that is more severe depends on the circumstances, depends on the situation. So I gave you 2 examples here. In a jury trial, okay, you've heard the phrase innocent until proven guilty. In our judicial system, the foundation is that we assume someone is innocent until we can establish that they're not. Okay, we use the word proven, but don't we all know that there have been some innocent people sent to jail? They literally have like organizations that spend all their time and money trying to get people like that out of jail, okay? Presumed innocence is the null hypothesis. If you reject that claim in favor of the alternative, you're rejecting the innocence in favor of supporting the fact that they are not innocent, okay? But if you end up convicting an innocent person, you have committed a type 1 error. A type 2 error is you fail to reject the null hypothesis. So you stick with it. You say, okay, I'm going to say that he's not guilty. I'm going to stick with that. And then later on, you find out that he is. Okay, you failed to reject, and later on you found out, dang, he was guilty. Okay, our judicial system is actually based on a foundation that we would rather let a guilty person walk free than incarcerate an innocent person. Okay, so as much as we don't like seeing innocent people go free, that is considered favorable to locking up one innocent person by mistake. Okay, that's how our judicial system is, that's the foundation. That's why we start with the presumption of innocence, and the whole proof, the burden is on the whole proof is on the prosecution to establish why they should be considered guilty. Okay? Our judicial system essentially is based on the premise that a type 2 error is preferred. However, in a medical setting, okay, the null hypothesis is typically that someone is healthy. The alternative hypothesis is some diagnosis. Okay, so if you fail to reject the null hypothesis, meaning I'm going to say you are healthy, and later on you find out that you weren't, you had cancer, whatever. Okay, a type 2 error is pretty bad there. Okay, a type 2 error is pretty bad, telling someone you're healthy and they're really not. As opposed to, have you ever had it like someone puts you on antibiotics, they tell you, oh yeah, I think you have strep throat. You go on antibiotics and later on you find out, oh no, you really don't. Do the antibiotics hurt you that much? Not in the long run. Okay, so in the medical setting, a type 2 error could be fatal. Okay, and I use the example of my nephew who has CF. When he was born, he wasn't diagnosed right away. He was just at first listed as failure to thrive. He was not gaining weight. He was throwing up all his food. It took them months before he got diagnosed with CF, and that they could now determine that was, so those weeks or months literally could have been fatal for him, because they kept saying, oh no, he's good. Okay, and he wasn't. All right, obviously we would prefer to reduce the chances of making any errors, but you select the level of significance based on these concepts. The probability of a type 1 error is exactly equal to your significance level. Okay, type 1 error, the probability of type 1 will be equal to alpha. The probability of making type 2 error is going to be called beta. If the consequences of type 1 error are really bad, like in our judicial system, then what we do is we reduce alpha. You use a smaller alpha if you're trying to reduce the type 1 error. Alpha and beta are not complementary, but they are inversely related. So every time you reduce alpha, you are going to increase beta. Okay? When you fail to reject a null hypothesis, you commit a type 2 error potentially. You might wonder whether the null hypothesis really was false and your data just didn't support that. Your data didn't detect it. The test's ability to detect that false hypothesis is called the power of the test. If you think about it, if you're trying to figure out whether I have to reject that 80% claim from that basketball player, I want my test to be powerful because I want to know, is he really an 80% free throw shooter or is he not? I want a powerful test that will give me the right answer. Okay. The power of a test is the probability that the test correctly rejects a false null hypothesis. If failing to reject the null hypothesis, when the null hypothesis is false, so you should have rejected it, that's type 2 error, that's beta, power will be its complement, 1 minus beta. Oh, we got to put some stuff in the chart because I know there's a lot of stuff going on. So go back to the chart. Type 1 alpha. The probability of type 1 is equal to alpha. probability of type 2 is equal to beta. And the power of a test is rejecting the null hypothesis when you find out that the null hypothesis really was false. So you really were glad that you rejected it. So this smiley face also gets labeled as power. And power is 1 minus beta. And in the same way that this is 1 minus beta, you could probably call this 1 minus alpha, but this tends not to be considered. Again, these are not like completely complementary. Alpha and beta don't add up to 1, but as you decrease alpha, you will increase beta. And what you need to understand is, if you decrease alpha, you increase beta, but if beta gets bigger, 1 minus beta gets, so your power just got smaller. Every time you change one of those numbers, whether you change alpha or beta, something is going up and something's going down, okay? And that's the balance. When people say, well, why wouldn't I just automatically go for the highest power I can? Well, if you go for higher power, that means you're doing a smaller beta. That means you're doing a bigger alpha. And alpha is the probability of type 1 error. And if type 1 error is really bad, I don't want that to be big, okay? It is a total balance, okay? Your book says to maximize the power of a test, you go as high on alpha as you're comfortable with, and then you try to get as large of a sample as you can, because a larger sample, this makes sense just intuitively. Doesn't it make sense that the more data you get, the larger your n size, the better your test is going to be? Okay, so all of a sudden, you now got to consider a larger n size. All right, so last example. You conduct the following test at a 1% significance level. All right, so alpha equals 0.01. Okay, so if alpha is equal to 0.01, I chose a really small alpha. And that means I must be really worried about type 1 error. Okay, so I chose a very small alpha because I'm really concerned about my type 1 error. You learn that the power of your test, if you're testing specifically at 6.2, the power is 0.24. You will at times have to explain what power is. Assuming mu really is 6.2, this test would have a 24% chance of correctly rejecting the null hypothesis of mu equals 6. Now, pay attention to the fact I gave you that power value based on specifically testing against 6.2. Okay, 6.2 is definitely not equal to 6. Okay, so 6.2 not equal. So I'm talking about I would be rejecting the null hypothesis, and power is the probability that you do correctly reject that null hypothesis. Okay. Now, what if you did an alpha of 5% instead of 1%? Now, I don't exactly know what the power would be there. This question isn't asking about that. This question is just saying, if you did 5% alpha instead of 1% alpha, would the power increase or decrease? So if alpha increases, what will beta do? that will force beta to decrease because they're inversely related. But if beta decreases, what happens to 1 minus beta? That would now increase, and that is the definition of power. So the power would increase. So I don't know what that power would be, but if the power to test at 6.2 is 0.24, I know that if I tested that same thing at a 5% level of significance, I would get higher power. Now, I was talking about this as if mu was 6.2. What if mu was 6.3? Okay, that's still not equal to 6. The question is, do you think if there were no other changes to your testing procedure, do you think the test would be more powerful testing for 6.3, or was it more powerful testing for 6.2? And this one's hard just because it is so intuitive. Okay. I always tell people on this one, think about on a number line. Okay. If your null hypothesis is 6, okay, 6.2, think when you graph, okay, if you're trying to graph something specifically, 6.2 is awfully close to 6, right? The farther you get away from the 6, the easier it's going to be to tell them apart because the gap gets wider. So if you switched and focused on 6.3, this will gain you power, okay? This will gain you power. The power would now increase. The farther you are from that null hypothesis, the bigger the gap, the more likely it is that you're going to be able to actually differentiate and say, oh my God, that gap is so big. And the probability then will come larger, okay? The farther you get from that null hypothesis value, the more powerful it's going to be because it's just easier to recognize the gap that's created. That's the best way that I've always thought about it, okay? If you're trying to test 6 versus 6.1, they're so close together, we can barely tell. But if you want to test 6 versus 6.7, you're like, oh yeah, it's way up there. Okay, the farther you get, the easier it is to tell. All right, so again, this is all background. This is all background. This chapter is set up like the last couple. Overview, and 9.2, we are going to learn how to do testing with proportions, like an 80% free throw shooter. Then in 9.3, we're going to learn how to do testing with means, with mu's, okay? So, by the way, chapters 10, 11, and 12, I think all 3 of them have only 2 sections, okay? So this is going to end us for quarter 3, but then quarter 4 for us goes really fast because I think there's only 6 sections altogether. So keep that in mind. So this handout, and it was supposed to be copied back to back. I just forgot to put something on the copier. But this handout, just one year, I made up a chart for each of 4 examples of type 1 and type 2 error. So the first one is the innocent versus not innocent jury example, like I already talked about. The second one is the medical example, like I already talked about. But the next 2, kind of interesting. I have an example of a snow day, okay? I once took a class from a guy who was a superintendent in Saginaw, and he said calling snow days was his least favorite thing in the world. Because he said, if you call the snow day and the snow is really bad, he goes, great. He goes, obviously a normal day, you don't call a snow day because the roads aren't bad, great. He says, but if you called a snow day, remember the last Wednesday, like it barely snowed at first. Okay, it was a teacher PD day. They canceled our professional development. It didn't start snowing until like 4 o'clock that day. Had they called a snow day and then it barely snowed, Okay, the superintendents get all sorts of complaints. But then there's the reverse. What if they don't call a snow day and it ends up pounding us? Then the parents are in an uproar because you put my child at risk, blah, blah, blah. Okay, type 1 and type 2 error. All right. And then my last one, this is a fun one. Buried alive. Okay, if you bury a dead person, that's okay. If you don't bury someone who's not dead, that's okay. But if you bury someone who's not dead, and if you don't bury someone who is dead, well, that's probably okay, just get snow. Okay, so type 2, type 1 error, which one's worse? Okay,